Hello everyone, my name is Timothy Mwewa Joseph. In this video, I'm going to teach you some calculations in simple harmonic motion. So after watching this video, you'll be able to calculate length of a helical spring or spiral spring, and also calculate acceleration, and then finally find time period of simple harmonic motion. So let's begin. For any oscillating object, the resultant force acting on the object acts towards the equilibrium position. The resultant force is described as a restoring force, as it always acts towards equilibrium. So just like what you can see in this simple harmonic motion, so it is oscillating, there is a force that is making this to happen, and that force is known as resultant force, which is also known as restoring force, because it is responsible for making this object to move to and fro, and also to restore it back to equilibrium. And the equilibrium is simply a balancing position. Again, provided the restoring force is proportional to the displacement from equilibrium, the acceleration is proportional to the displacement, always acts towards equilibrium. Therefore, the object oscillates with simple harmonic motion. Let's proceed. So, when a weight is attached to one end of a suspended spiral spring, it expands. According to Hooke's law, the restoring force F in the spring would be directly proportional to the extension E produced, provided the spring is not deformed. So, according to Hooke's law, the restoring force F in the spring would be directly proportional to the extension E produced, provided the spring is not deformed. The spring is not deformed means that it does not go beyond elastic limits. If it goes beyond elastic limits, so we are going to have another story in this. The restoring force F is given as Ke minus Ke, where K is the spring constant, and therefore we have mg equal to Ke. So take note of this simple equation or formula. We are going to make use of it later in our calculation. So let me briefly show you in diagram. Look at this diagram. According to Hooke's law, this is a helical spring. So there is no load attached to it, so there is no extension. We have zero extension, zero distance. So sometimes extension can be represented by letter X or E, yes, as we can see in this diagram. Okay. So but when a certain amount of mass is attached to it, which is the load, so the spring expands or extends, and then there is a certain distance, extends gets to a certain distance x here. So, and then we double the load again, we also see further expansion or extension. You can see when we add another load on it again, so we have 2 times the distance here, 2 times of the distance here. So Hooke's law, which states that the force F needed to extend or compress a spring by some distance x is proportional to the distance. And we've got this guy here, our force, which is the load attached to it. If you want to find the force or the weight of the load, is given as Ke, similar to this. So it's still mean the same thing here. So Ke, so I don't forget, I say this is the distance or displacement or the extension. So still mean the same thing. So we are still saying the same thing here. Okay, let's go and solve some questions. Our period of oscillation T is given as 2 pi divided by angular velocity. Angular velocity. When we have just like in a simple pendulum period like this one, or sometimes we can have 2 pi roots m over k, where our m is mass and this k constant, spring constant. So we can either use this equation, we can also use this equation, depending on the parameters or values that we have in our question. So let's look at this question. A spring of natural length 300 millimeters hangs vertically with its upper end attached to a fixed point where a small object of mass 0.2 kg is suspended from the lower end of the spring in equilibrium. The spring is stretched to a length of 379 millimeters. Calculate the extension of the spring at equilibrium, the spring constant, the time of oscillations that the mass on the spring would have if the mass was to be displaced towards downwards slightly, then released. Okay, let's see. So I'm just quickly do the diagram of this. I show you the diagram. So we have our spring. Spring. Let's see. We have the spring here. The spring. The spring. The spring. The spring is just the length from here to here. Um, is what? So got a length is 300 millimeters. 300 millimeters. But when a load of 0.2 kilogram was attached to it, so there's an extension, more extension, something like this. So let's say this is the load. This is our load here, 0.2 kilogram attached to it. And then we have a further extension from here to here. See, so then the spring now extended, stretched to 379 millimeters. And then the question is, so this is millimeters too. And then the question says we should find the extension of the spring at equilibrium. Okay, when it balances. So at equilibrium. So this is very simple to calculate. So let's just clear this and then we start our calculation straight away. Let's go. So extension of spring at equilibrium is given as 379 millimeters minus 300 millimeters, which is 79 millimeters, as you can see from the diagram I drew before. How do we get this? So final extension, final length of the spring minus initial length of the spring gives this. So that's what we did here, and then we arrive at this. But now we must change our value into meters so that we not have problem in our calculation. So for us to do that, you should know that 1 meters equal to 1,000 millimeters. Really? Yep. So that is why we divide 79 millimeters by 1,000 meters, and then when we do that division, we have 0.079 meters. So this is our extension here. Okay, meter. Then spring constant. Spring constant, we are going to make use of this equation. This equation is gotten from here. We say the mass of the object is directly proportional to this spring constant. So for us here, what we do, we just make K subject of the equation or subject of the formula, and then that is how we got this value. So we substitute our value again. So we have our mass, which is 0.2 times 9.8, and then divided by the extension P, which is 0.079. When we do that calculation, we arrive at this 24.8 Newton per meter. So don't forget your unit. So it's very important. So we arrive at this answer. And then let's go to the next question to calculate our time period. So here we are using this equation because in our question we don't have angular velocity. So we cannot say we are going to say to use this equation or this formula. We can use this formula because we don't have angular velocity in this question, so we cannot use this. So we are going to make use of this. We have mass and then we have spring constants. So let's go. So we have 2 times value of pi, which is 3.142 divided by square root of the mass and then the spring constant. So we have put everything here, and then do I need to finish this calculation? Okay, if you want me to finish it, so let me just complete the calculation. So let me clear the screen. So 2 times 3.142. So I'm going to put everything here. So we should have something like this. Our time is equal to 6.284. Hope this is correct now. Okay, then we are going to take the value of this, and then we'll take the square root. When we do that, we are going to have times. Okay, let's check calculator and see what we have. Okay, so we have 0.0891, and then our time period is now 0. When we multiply everything together, we should have 0.56. Our units second. Do not forget. Some questions will require you to put your answer in standard form. So this is in 2 decimal places. So when you're asked to do that in standard form, so it's going to be 56, right? Times 10 raised to the power of -2 over 2 seconds. So in standard form, so this is our time. Hope this is clear. Yes. Okay, let's move to the next one. Let's move to the next question. So I'm going to clear the screen. Next question. We need you to come out. Okay. So this is our question 2. A long and light helical spring is stretched to 4.68 centimeters when a given mass is hung on it. What is the period of vibration of the mass if pulled down a little and then released? Okay, so here we're looking for period of vibration. So let's start our calculation again as usual. So we are going to write our solution, and then we bring out the parameter. So solutions. What do we have in this question? So we've got the length, which is 4.68 in centimeters. And then what do we have again? Okay, I think we should have acceleration due to gravity, which is constant. So 9.8 is, we have to use it, meter per second square. My goodness. Okay, what do we have again in this question? Then we are looking for our time period. So we don't have this guy, time period. So we need to find it. It's missing. We need to find it because it's missing. So we need to find this guy. Okay, so what formula are we going to use to do this? So our formula now, our time period is equal to, okay, sorry, I don't want to change. I like using different colors. I love this, and then I pick this. So, no, not you. You need to go back. Respect my command. So our time period that we're going to use is equal to 2 pi, then root length divided by g, acceleration due to gravity. So this is the formula we're going to use for time period in this case. Yes, please take note of this. And so let me bring everything here. So we substitute again our value. So our time is equal to 2 times the value of pi. Yes, and then we take the square root of the length Length, yeah, I need to explain. So length is given in centimeters. So we need to convert this to meters. So for us to convert into meters, we say 4.68 divided by 100. Why are we doing that? Because 1 meter is equal to 100 centimeters. So we are going to have 0.04, yes, 68 divided by what? 9.8. Yeah. So this is what we're going to have, and then we can go ahead to simplify. So when we simplify, look for the value. 2 times 3.142, we should have 6. No, I need to get rid of this. Don't spoil the show. Okay, so we are going to have 6.284 times the value of whatever we have here. So let's check calculator. Can someone tell me the value? So we should have, what do we have? 0.0693. Okay, 0.0. No, I asked you to write 0, not 6. Okay, so 0.0693, and then let's multiply it together. Can someone quickly punch calculator and tell me what is the value? So everything gives 0, goodness, 0.43. So these are time period. And then we need to put our unit seconds. So this is it here. Very simple. So just remember this formula. Yes. So you've got a different formula, yes, to remember for a successful calculation. They are very simple to remember. Yes. The other one, you just need to put M here and put your key here. So it's very simple. So once you remember this, you can remember the other one. Okay, let's move forward to another question. So another question is this. Yeah, this is another question that we're going to consider. Compute the acceleration due to gravity at a place where a simple pendulum 150 centimeter long makes 100 vibration in 246 seconds. Oh, so here we are going to calculate acceleration. Yes, from the formula that we just used in question 2, we can also use that to calculate our acceleration. So when we make a G the subject of the equation. So let's start again. So what do we have in this question? Solution. What do we have? We have our parameters or the data that are given. So we've got the length of the simple pendulum is 150 centimeters. Don't forget that we always divide this guy by 100. So let me help you write it here. When we do that, what do we have? Dun, 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 dun. Are we going to have 0.015 meters? Yes, we should have this guy now. 0.015 meters. Okay, then we need to find acceleration, but we have it makes 100 vibrations in 246 seconds. So our time period is going to be what? Yes, yes. Time taken over the number of vibration. Yes, time taken over the number of vibration. So time taken is 246 seconds, again divided by 100. So we should have 2.46 seconds. Goodness. So which means that it takes the pendulum to make it takes 2 minutes 46 seconds for the pendulum to make 100 vibration. So interesting. Okay, let's go ahead to calculate what do we call it now? Our our acceleration. Let's calculate the acceleration now. So we are going to make use of this formula. So acceleration is going to be g equal to 4 pi square multiplied by length, and then we divided by t square. Okay, don't be confused. This equation is gotten from this equation, that is time is equal to 2 pi root length divided by acceleration due to gravity. So if you want to make g subject of the equation, you need to uh, multiply both sides by, when you start to change your subject of formula in this. Please, you need to study that. So I'm not going to do this for you here. So that in order to save time. So you multiply both sides by, take the square root of both sides, rather taking the square of both sides, and then, or take the square of both sides. When you take the square of both sides, then this will go out, and then you can arrive at this. So that's another topic on its own. So let me not deal with that here. Okay. So let's take away this. So knowing that, then just, okay, let's just input your value into this equation. So we have our g, g equal to 4 times the value of pi. The value of pi now. So our pi is, okay, let's 3.142 square times what again? Do we have length? Gracious Lord. Length is 0.015. Then divided by what? Can you complete this by yourself? Complete this by yourself and let's see what you get. Oh my goodness. Oh my goodness. Oh my goodness. Oh my goodness. I have made a mistake. What's wrong with me? I just realized that, so this is why it's good to have students around sometimes. So they quickly say, oh, Mr. P, you have made a mistake. So let me get rid of this. That is a mistake. Okay. So this is going to be not, so this is 100 meters, 150 divided by 100 meters. So it's going to be 1.5. Come on. Don't know. 1.5 meters. What's wrong with me? The calculator in my brain is not functioning well. Am I correct? 1 meter equal to what? Oh, 100 centimeters. What's happening? Oh, goodness. Okay. Yes. Yeah. Now we're correct now. So let's continue. Don't worry. I'm just waking up from sleep. So my brain is still booting. So, okay. So we've got 1.5 here. Then divided by t squared. What is t squared? What's time? Hope there's no blunder in this too. No blunder. You are safe. Save. If you want to bracket, come brackets. Okay, let's put square. Okay. So what do we have? Let's punch calculators. Punch calculators. Here, inside this value. Using that. So 4 times rather. What do we have? 3.142 square. 3.142 square. Tell us. Okay. We've got 9.9. So we're going to put 9.9 here. 9 points. 9, excuse me, where did you get this? Times 1.5. How am I repeating this? Okay, for clarity purpose. Then 2.46, right? Square, what is the value? 0.00. Did I say 0? No, 6.1 approximately. 6.1, okay. 6.1 or 6.5. Don't give me a wrong value. 6.1. 6.1. Okay, so acceleration now will be equal to, so let's multiply everything together and then get our value without wasting much time. 4 times what? 9.9 times 1.5, and then we divide the value divided by what? What do we get? Divided by 6.1. Bam. Got 9.7. Is this correct? 9.7? 9.7, 9.7. Okay, let's write it here. Yeah, it's correct because that's our acceleration due to gravity. Yeah, it's correct. So approximately is going to be 10 meter per second square. Yes, this is correct. Yeah. So we have 9.74. 9.74. And then we put the units meter per second square. Square. So this is our acceleration due to gravity. So you can see, so this is how to calculate gravity, but you must always remember the formula, and they are very simple to remember. So we are going to stop here. Please, I need you to remember everything that you have learned. Look for some questions, practice. If you have questions, send your questions to me. I'm going to answer your questions. And if there's anything you don't understand, ask. I'm also going to answer you. So you can use the chat box, put down your comments. Please like this video, share, and also subscribe for updates. Thank you for taking your time to watch. Goodbye. By now, you should be able to calculate length, gravity, and time period. Okay, please let me hear from you. Bye bye. Thank you.